chapters kind of go hand in hand, so we're going to be talking about them kind of at the same time. And we've talked quite a bit about much of at least chapter 8. So in chapter 8, there shouldn't be just a whole lot of surprises, but we've got a couple of different things, and even though they're interconnected, interrelated, they're quite different. Okay, so we have X-ray creation, that's X-ray production. We have X-ray emission from the X-ray tube. And what these two chapters are the factors that affect the emission and production of X-rays. Okay, so we're going to go all the way back to the first lecture and talk about how X-rays are created in two different ways we create X-rays. And then we're going to talk about the creation and the kind of the distribution of the energy levels of X-rays at creation. And then we're going to talk about how they're emitted from the X-ray tube and how that differs from creation. Okay? So if you remember the way that we talked about creation of X-rays, we had two different ways that we recognized we created X-rays. Both of them involve conversion of one type of energy to another, right? So what we create on the filament is space charge, and that's just a whole lot of electrons. And once we have kVp, we send the electrons across the tube to interact on the target, right? So all the electrons are essentially the same size. Now you can get into the minutia of, say, the theory behind the reason why it is that nothing can travel faster than the speed of light is because the closer you get to the speed of light, the larger something gets. So you can say, well, if they're traveling at half the speed of light, they're going to be larger than what they are at a third of the speed of light. Okay, whatever. Let's just pretend that they're always the same size, right? So when we accelerate the electrons across the tube, the only thing that's different is the speed with which the electrons travel. If you remember the different types of energy of motion was what? Stored energy, that's potential. Kinetic, right. So we release the potential, the electrons travel across the tube. They're carrying with them kinetic energy. So the loss of that kinetic energy is how we get most of our X-ray beam. So if you remember, electrons, the mass of electron compared to a proton and a neutron is very small, right? And we gave it an electron or a elemental mass number of what? Zero. Yeah, it's so small that we didn't even recognize that it almost doesn't exist, right? And the electron, or I'm sorry, the elemental mass of a proton and a neutron were 1, right? So exponentially larger, significantly larger. So all of the mass of an atom is contained within the nucleus, pretty much, right? So what we've got in the nucleus of the atom, we've got protons, we've got neutrons, and we've got electrons around the outside. Also, we said that the area inside of an atom is primarily, it's not the mass, this is the area. Kind of like the solar system, it is empty. There's nothing there, right? So when I draw this is much condensed so that, perceptive-wise, if we were looking at an atom, our inner shell electrons would be very much further out than this. If we're looking at a hydrogen atom, the neutron or the proton being here, the first set of electrons would be way out there somewhere. Right, so almost nothing there. And in that almost nothing cloud, we got these things that are so small that they almost don't exist. The protons and neutrons, much larger than those, but they are still so small you can't see them, right? So what we're doing fundamentally is we're shooting electrons, which are so small that they almost don't exist, at something that is so small that you can't see it. Right? You follow me? So the likelihood, you can't really focus those electrons directly to the nucleus of the atom, so it's a numbers game, what we're doing is we're shooting these electrons across the tube to smack into this thing. Most of those electrons are going to pass so far away from the nucleus of the atom because, you know, in this diagram here, if those are electrons, the nucleus is only going to be about that big. It's going to be tiny. So the chances of hitting that thing are good? No, not very good. Not very good at all. As a result, most of the electrons pass so far away from the nucleus of the atom that they barely lose any kinetic energy. So the way we create X-rays, two different ways. We've got Brems, and with the Brems, what we've got is truly just loss of energy. So we send electrons across the tube really, really fast. If they change directions a little bit, they're going to lose some energy. If they change directions a lot, then they're going to lose a lot of energy, right? So back in the early portion of the semester, we talked about things like comets and asteroids and whatnot coming through the solar system, right? We talked about Jupiter picking those things up, and they impact on Jupiter as opposed to hitting the Earth. Why? Comparatively speaking, Jupiter is much larger, right? So greater gravitational pull, right? So using that, if we send a projectile electron that gets close to the nucleus of the atom, it's going to lose more energy, right? So if this one out here comes in with 100, we're going to call this KeV, but it's really essentially the same magnitude of energy. 100 KeV worth of energy, that's kiloelectron electron volts. And it changes directions just a little bit, and that same electron leaves, and it didn't touch anything, it just leaves, and it's got 10 KeV. Oh, no, just did that completely backwards. Let's say it's got 90 KeV worth of energy. Did it lose energy?
Yes.
Yeah, it did. And where that energy is going to go is it's going to go, and it can go off in any direction, but it's going to leave in the form of an X-ray photon. Okay, so that X-ray photon, the energy level of that X-ray photon is going to be equivalent to the difference between incoming and outgoing energy. So that X-ray photon is going to be, now we're going to call it KVP, is going to be what? 10, right. So it's going to be 10 KVP. Okay, so now this guy comes across the tube, and it's closer to the sun even, so even a greater gravitational pull than, you know, the difference between Earth and Jupiter. It gets close to the sun, massive gravitational pull. This thing makes a sharp turn, and it leaves, it's still an electron, it leaves, it came in with 100 KeV worth of energy, and it leaves with 10, okay? So what's going to happen to that other 90 KeV? It's going to kick off in the form of a photon, right? And that photon is going to be 90 KVP X-ray photon, okay? So it's breaking, it's slowing down. The electrons entered the nuclear field, but they didn't interact with any electron. They didn't necessarily even hit the nucleus of the atom. They just lost some energy. As they lost energy, we get X-ray creation that's equivalent to incoming and outgoing energies of that electron. We still have an electron. Now, can that electron go on and interact with another atom, get close to the nucleus of the other atom, and lose all of its energy so that it had 10 coming in and effectively it's got none going out? Could that potentially happen? The answer is yeah, it could. So one projectile electron, depending on how much energy it loses, it could undergo this interaction multiple times inside the target and give you more and more X-ray photons. Okay. Now this one's only going to be a 10 KVP X-ray photon, right? So it's very low energy, and we'll talk about that here in a bit. Okay. So that's one way, and that's what we call Brems, and that's short for Bremsstrahlung, right? This just means slowing down or breaking. The projectile electron slows down, loses energy, kicks off an X-ray photon equivalent to the incoming and outgoing energies, right? Brems. The other is characteristic. And characteristic occurs when we have interaction, and rid of the X-ray photons, but I want to get rid of some of this traffic. When the projectile electron strikes an orbital electron. All right, so projectile electron. Remember, projectile electron, the electron is always a straight line, right? X-ray photon has the wavy thing, right? So projectile electron strikes an orbital electron, and if it knocks it, if it's carrying enough kinetic energy, if it's got 100 keV worth of energy, then it can strike that, and this is held into place with a specific keV. And if this overcomes that, then we can eject that electron. Right? And really the keV is a better measure of binding energy, but let's just go with it. Okay? So we eject that electron, and what we know about the atomic structure is that's not a good, not the healthiest environment for that atom, right? We have created a, what's that? Ion, right. We ejected an electron. If we get rid of a negative charge, then the whole atom becomes positive, right? And we created two ions, the free electron plus, the rest of the atom as a ion pair. Very good. So we eject that thing. It's going to want to replace it, and it can replace it from a lot of different things. All right. So remember, we've got binding energies that are specific to the shell. Innermost shell is K shell, and because of how close it is to the nucleus of the atom, you remember talking again about the solar system and the centripetal and centrifugal force that a planet has to have in order to stay in its orbit. And we talked about Mercury. Where is Mercury? Closest to the sun. It's just screaming around the sun really, really fast, right? So it's got to be bound in really, really tightly. But then we talked about the outermost, Pluto, right? Poor Pluto. It's a planet, not a planet. It's a planet, it's not a planet. It's very loosely bound, right? And so it wouldn't take as large and fast-moving of a comet or whatever to knock Pluto out of its orbit as what it would Mercury, right? So the further out we are, the less binding energy we have. And what kind of atom do we use for the target? Tungsten, right. So the inner shell binding energy is 69.5 keV in a tungsten atom. The next one out, I think, is 12 point something, all right? So, and the next one, I think, is down to 3 keV. Okay, so the numbers don't necessarily have to be exact here. The point is that if we knock this one out, what we could have happen is a number of different things. Okay, so the binding energy here being 12. Okay, let's think back to our Brems, the high energy Brems that we created. What was the energy level of that that electron after it underwent that first turn? What was it? We lost 90. We came in with 100. We lost 90. That electron had 10, right? So 10. So what is it bound to, though? Let's start with that. What is it bound to? If it's floating around in the nucleus? Nothing, right? It's not bound to anything. So if we've got a space that's drawing in 10 keV worth of energy, and we've got this electron that's buzzing around with 12 keV worth of energy, and we've got this thing that's buzzing around with 10 kVp worth of energy, could it slip into that? Yeah, but it's not bound to anything. But this force could draw that in and lock it into place. It's a free-floating electron that locks into place. When that happens, we eject an electron, so we got a free-floating electron there. We drew in a free-floating electron from here, and what we're going to do is we're going to cast off an X-ray photon equivalent to the binding energy of the electron that left and the electron that took its place. Okay, so what was the binding energy of the electron that left? 12. What was the binding energy of the one that took its place? Binding energy. I just use that 10 for, let's get rid of that to get rid of confusion. What's a binding energy? What's it bound to? Nothing. It's bound to nothing, right? But if it snaps it into place, then what we have is an X-ray photon that's created that's equivalent to the difference in those binding energies, okay? So mathematically, what does difference mean? Subtraction, right? So binding energy of the electron that was there was 12, minus binding energy of this one was nothing. So 12 minus 0 is, that's 12 kVp X-ray photon. Okay? Difference in binding energies for characteristic X-ray photon creation. All right? So then let's take a look at this. Let's get rid of all this, and maybe these two will kind of make a little bit more sense. Let's say this electron is here, so that our projectile electron just hits the inner shell electron. Okay? If we have 100 kVp worth of energy, keV worth of energy, hitting 69.5, what's going to give? What's going to happen? Yeah, you've all played pool, right? You know, I mean, if you roll a ball hard enough that it just to where it touches it, does it knock the other ball around? Where it just barely touches it? No. So what you have to have is enough speed on that ball to overcome the gravitational pull on the ball to knock it around, right? Binding energy, 69.5. Incoming electron, 100. Could that overcome this? Answer is yeah. You just smack that with a pool stick, right? So you hit that, and it takes off into a different direction. Binding energy there is 69.5 keV. Okay, so you got an electron that's floating around out here. That electron may go off in a different direction. Okay, so you've created an ion pair. What's the binding energy here? What would we say it was? 12, right? So it's 12. So could that pull that one into place? Yeah, 69 is greater than 12, right? So it could grab that electron and pull it into place. And if it does, we got an X-ray photon equivalent to the difference between 69.5 and 12. So we got about a 57 kVp X-ray photon. Okay, difference in binding energies, characteristic. Why do we call it characteristic? It's characteristic of the tungsten atom. If we used anything else, any other element, what would that do to our nucleus? It'd change it, right? It'd either be bigger, fatter, heavier, or smaller and less heavy, right? So what's that going to do to the gravitational pull of the nucleus on that inner shell electron? If it gets bigger, that gravitational pull is going to go up or down? Up, right? It's going to go up. So it's going to have a higher binding energy, right? So characteristic, that inner shell electron binding energy is always going to be 69.5. Always going to be 69.5. It's characteristic of the tungsten atom. Change the type of atom that you're using for a target, you're going to change that characteristic interaction. Okay, so let's do this one more time. So if we knock this one out, right, and we said binding energy it was 12, and it pulls one from here, are we going to create a characteristic X-ray photon? I know what some of y'all are thinking. You're thinking no, because which is the only one that we really recognize?
The K-shell?
K-shell. But are we going to create an X-ray photon? The answer is yeah, we are. And that X-ray photon is going to be the difference in those binding energies. So we're going to knock that, knock that electron out. I'm going to snap that one in place, and it's going to be 12 minus 3, and that's going to give us a 9 kVp X-ray photon. Is it useful? No, not at all. But do we get one? The answer is yeah. Okay, so let me show you this. If you flip over to, this is why I really think that this should be a single chapter instead of multiple, for one of the reasons anyway, is the different, if we change our target atom, all of that's going to change. But with the tungsten atom, if you look on page 137, you see all of the potential characteristic X-ray interactions or X-rays that you can create off of a tungsten atom. So you've got all the way up at 69.5, and that's the highest energy. Okay, everything else is below that. So if you have an inner shell, a K-shell electron that's ejected and it's replaced with a non-bound electron, then you're going to create the maximum characteristic, which is going to be 69.5. Okay, always 69.5 when we're talking about characteristic X-rays. But in Brems, because what we're shooting are things that are so small that they almost don't exist, it's something that's so small we can't even find it, right? Most of them are going to pass at a distance from the nucleus, and what we're going to have are X-ray photons. In the Brems, let's say we set 100 kVp on our control panel, 100 kVp, then our Brems X-rays that we create are going to be everywhere from effectively so small that we're just going to give it so low energy that we're going to give it 0 kVp all the way up to the maximum we can lose. Okay? So we're going to create X-rays in the Brems spectrum from 0 to 100. With a characteristic, we're going to create several. We're going to create several, like the chart on page 137 indicates, figure 8.9. We're going to create several, but we're only going to recognize one, and that's 69.5. Now we're going to, if this wasn't theoretical enough, we're going to talk about this even more theoretically. Okay, so statistically speaking, I don't know how they measure this, but statistically speaking, they say that the Brems creation accounts for 85% of X-ray beam, and characteristic accounts for 15%. That's at 100 kVp. Okay, so at 100 kVp, the higher the kVp goes, the more efficient X-ray creation is. X-ray creation, if you remember, is very inefficient. The main thing that we create is heat, on an order of about 99% heat, 1% X-rays. So of those 1% X-rays, 15% are characteristic, 85% are Brems at 100 kVp. If you reduce your kVp, it gets less effective, less efficient. If you reduce your kVp enough, let's say our kVp is, we set our kVp at 50 kVp, we're shooting a finger. Well, what do you got to have in order to eject the inner shell electron? It's just bound into place with 69.5 keV. If keV and kVp are essentially the same type of force or same magnitude of force, what do you have to overcome that binding energy? 69.5. So you set your technique at 50 kVp, and what are you not getting? Characteristic. Okay? Again, theoretically. Are you getting characteristic? Yeah, just not in the characteristic spectrum, the characteristic energy level that we care about. The 69.5, we're not getting that, right? So, what we're going to talk about on Friday is the distribution spectrum. So in the distribution spectrum, everybody good with this? Okay. I need a bigger board. And I know I got another one over there, but again, if I put it in the middle, then everything's going to look wonky. So in the distribution spectrum, what we're going to look at on Friday is everything that affects emission from the X-ray tube. So in the distribution spectrum at emission, and I'll explain all this on Friday, what you have is overwhelmingly, we have Brems X-rays, okay? So if you see a distribution spectrum, what it looks like is kind of an elongated bell curve. This end of the bell curve is very steep. That end is more tapered. Okay, and what this tells us is the energy level of the X-ray beam as opposed to the number of X-rays that we create. I'm going to go through what happens when we change kVp, when we change mass, when we change filtration, and all that as well. But this is the Brems spectrum, okay? The characteristic spectrum, in order to have a characteristic spectrum, our energy level has to be at least 70 kVp, right? You're not going to see a Brems spectrum on a test that's like 69.4, you know. How you can tell that you've gotten to 70 kVp, 69.5, 70 kVp, is whether or not you have a spike on it. So if we're at 70 kVp, what you're going to see is a spike. Right? That spike represents the characteristic spectrum. So if you're looking at a distribution spectrum and it doesn't give you any numbers, what can you tell from that spectrum? And it doesn't tell you any of this, nothing. You just see that. And certainly you don't see this. What can you tell from that spectrum? What does spike represent? Characteristic, right? So what does what do you know about that? If it's got a spike, bingo, you're up to 70 kVp, right? So if it does not have one, it's all Brems, meaning that your peak energy is not 69.5, right? So distribution spectrum is where we're going to spend the day on Friday. And it's really how we're going to start next semester. If you can understand everything that affects the energy level and the quantity and quality of the X-ray beam, then if you can wrap your mind around that going into imaging, it makes imaging a whole lot easier. Because what we talk about next semester is what happens to your index number, what happens inside of your patient whenever you change your kVp, change your mass, and all that. Okay? All right, so X-ray production, loss of kinetic energy of the electrons, especially in the Brems. With characteristic, we have a little bit of other stuff. All the electrons have some degree of mass, but really the determining factor of what you're going to get is the speed of those electrons coming across the tube. The more speed they have, the higher energy of X-ray photon you can create. And speed is really a measure of kVp. So as you apply higher kVp, you send the electrons across the tube faster, they have more kinetic energy to lose. If they lose a lot of kinetic energy, you have a high energy X-ray photon, right? So with Brems, it's just a slowing down and loss of kinetic energy as opposed to characteristic. We've got removal of the electron, replacement with another electron. Brems, the energy of the X-ray photon that we create is the difference between incoming energy and outgoing energy of the electron, right? Closer it gets to the nucleus, the more energy we lose, the higher the energy of the X-ray photon we create. With characteristic, it's the difference in binding energies. Difference, in both cases, subtraction. Difference in binding energies, 69.5 on the inner shell, and they reduce as they go out. Okay? Highest energy you can create with Brems is whatever you have set. As long as your machine's working properly, you set 150 kVp, you'll get 150 kVp X-ray photons. What we'll talk about on Friday is that we're not going to get a whole lot of those. We get a lot of other stuff, but we're not going to get just a whole lot of those. Okay? The highest energy of the characteristic is always going to be 69.5. We're just going to say 69. So we have to get to 69 kVp in order to create that spectrum. Okay? Any questions on that so far? We're not done. I'm just want to know if you have any questions. No? Okay. All right. So again, the two chapters are really kind of interconnected, but they're two totally different things. So you have creation, X-ray creation, and that's what we're going to talk about here. And we'll talk about emission on Friday. So X-ray creation, you send the electrons across the tube. Most of them become heat. A very small percentage of them become X-rays. And it's all about loss of, primarily about loss of energy, in Brems anyway. So again, you've got a nucleus of the atom, is that big. You got these electrons that are lined up over here, right? And if they could fly in a straight line, if I could just grab them all together and let's just say that that's a complete dotted line, and I were to push it towards the nucleus of the atom, most of your projectile electrons are going to be close to the nucleus or far away? Far away, right? They're going to be far away. So since they're going to be far away, most of the Brems that we create are going to be very low energy. Okay? Now I want you to look at what Bushong has on page 87. And again, this is kind of why I wish he put them together, is because this is a little bit confusing. His ball analogy there is really emission, much more so than what it is creation. Okay? At the face of the anode, not only is X-ray conversion very inefficient, but the energy levels that we get are very poor. Okay, so if we were to draw on a line, if I could actually draw straight, if we could draw our creation spectrum, remembering that this is numbers and this is energy level, and these are X-rays that have been created, then what we would get is we get a tremendous amount of low energy X-ray photons, and very few, this is just numbers under here, and very few high energy X-ray photons. That's at the face of the anode. That's what your X-ray creation, if you could plot the number of X-rays that you created and the energy level that you create, that's what your creation spectrum would look like. Okay, so this being energy down here, what's missing on this? What do you not see? Huh? Heat? Peak. Yeah. Okay. Well, you talking about that spike, right? Yeah. So peak. Peak would be your kVp, your highest kVp. But what you're talking about is a spike, right? So what can you tell me about this creation spectrum? Very low energy. We haven't gotten to 69, right? Okay, so what if then, I shouldn't have drawn it that high up. Let's change this just a little bit, okay? Give myself a little bit more room. Let's say that the creation spectrum looks more like this, okay? So what then if I were to create, let's say that was at 50 kVp, what if I were to create one at 100 kVp? Okay, so kind of reverse engineering this, if we're going from the highest energy down to the lowest energy, first off, when you increase your kVp, do you focus those electrons, projectile electrons, to get closer to the nucleus of the atom? Have we talked about anything like that? No, it just doesn't happen, right? So it's still just a numbers game. So we're sending a lot of electrons across the tube, and the same interactions are going to happen. Now, the electron may penetrate a little bit further and interact with more nuclei, right? And give you more X-ray photons, but it's still, the peak energy is still dependent on those electrons that get close to the nucleus of the atom and lose a lot of energy, right? So just like at 50 kVp, our peak energy is going to be very low, right? But which X-ray photons might we stop creating if we increase our X-ray energy, our kVp level from 50 to 100? It's a trick question. I don't want you to think too hard on this. It's a trick question. Which ones we're going to not create anymore? Because we've focused those stream of electrons to point right at the nucleus of the atom, right? No. So which ones are we not going to create anymore? We're going to create all of them. Every one of the ones that we created before, we're still going to create them. The only thing we did was we added more down here. Okay? So, it's going to mess you up just a little bit. So, let me preface this with saying go with what Amy told you for intro. Okay? And I'm not, going to contradict Amy, but I'm going to dial it in a little bit closer. So on the test, if there's a contradiction between what I'm about to tell you and what Amy has taught you, go with what Amy said. Okay, because that's kind of the industry standard, but this is how it really happens. As you increase kVp, you increase the output from the X-ray tube. Okay, so you've probably been told what controls your numbers. I think I've even told you this. Mass. It's mass, right? But is it really? And the answer is no. Yeah, mass does, but mass is a direct measure, okay? What I mean by that is take a look over at the formula for kVp. If you flip over to page, chapter 9, the formula for kVp and X-ray intensity on page 146, what do you see? It says intensity, which is always mass, numbers, right? Intensity 1 over intensity 2 is equal to kVp 1 over kVp 2. In parenthesis, what? Square. Right, so where mass, you double your mass, what you do is you double your output, right? You shoot a chest X-ray with 2 mass, and it's not, your S number indicates you underexposed patient, you go back in and repeat the image and you use 4 mass, then you can reasonably expect to have exactly double the number of X-ray photons created. It's a direct relationship. With kVp, you shoot a chest, or you really mess up, shoot a chest X-ray with 50 kVp, and then you go back in, you reshoot it with 100 kVp. What's the difference there? How much of a change in kVp does it take to equal a doubling of mass? Have you all been through that? You should have.
Yeah.
15, we call that the what? 15% rule, right? 15% rule. So if you need to repeat an exam where you underexpose a patient, but you need an increase in penetration, you change your kVp by 15%, and it equals a doubling of mass. Okay, so I went a long way. That was a long walk to say, as you increase your kVp, we have a tendency to think, well, I just increased my peak energy. But what is all this? Numbers. We increase the numbers the number change is exponential. More than any other factor, when you change your kVp, you change your numbers. Okay? Now, why don't we say kVp controls quantity? Well, if you need a 15% change in the numbers, how much of a change in kVp are you going to use? You got to break out a calculator, right? If you need a 15% change in mass, how much of a change in mass are you going to use? 15%, right? 15, okay, 10% change. Let's get away from the 15% rule, say a 10% change. Then how much of a change of mass are you going to use? 10%, right? If you need a 10% change in your index number using KVP, I don't know. I have no clue as to how much to tell you to change your KVP. Full honesty, full disclosure, I have no clue. So it's a direct relationship. KVP exponential. It's a direct relationship. You increase your KVP and you increase numbers, right? It's a direct relationship, but it's exponential. 15% equals 100% change in numbers. Okay, I threw this on a class a couple of years ago, and it took them, I think, until about midway through the second semester to really understand what I was talking about. This is toilet paper math. Is essentially what it is. You go to the grocery store, you buy toilet paper. What does it say on the big package of toilet paper? 15 rolls equals 45 rolls, right? That's KVP. Okay, exponential. Just doesn't make sense. Exponential, direct relationship, exponential. Okay, so what else have we talked about this semester that could affect numbers? What's that? Filtration? Okay. Okay, I'm going to have to, you got into it a little sooner than what I wanted, but yes, filtration is in part where we're going to live on Friday. Okay, so filtration, how does it affect intensity? You add filtration, and what happens? Why do we have filtration? Get rid of low energy X-rays. Where on this graph are low energy X-rays? Right? Those are high energy. These are low energy. Right? So you change your filtration, and what's going to happen is you're going to get rid of these over here. Okay? So that eventually your distribution, and again we'll talk about that on Friday, your distribution is going to change. Okay? So right now we're talking about creation. Okay? So I'm going to erase this because we're going to talk about that on Wednesday, because creation and distribution are creation and emission are two totally different things. So what else have we talked about this semester then? So let's put them out here. KVP, mass, we'll go filtration here. And what else? Remember what that meant? Versus three-phase, right? Right? Yeah. Okay, so I'll tell you why I'm laughing here in a minute. So when we go from single-phase to three-phase, what do we have to do with our technique? We said that when you change from single-phase to three-phase, because all you got single-phase rectified, so single-phase rectified looks like this, right? And then you go three-phase and you kind of spackle all that stuff in. So what happens to your output? It increases, right? So, and this is why I was laughing, is because when I went through this before, I asked, and I think it was you, I asked what you expect your technique change to be. And logically, you're grabbing onto the one thing that makes sense in this class. Single phase, three phase, that's 1 to 3. Logically, you would think that your technique change would be a factor of, and it's not. It's not. How much of a change was it? 2. It's a factor of 2. Right. So in that, what we're talking about really is primarily, again, we'll talk about this on Friday, but primarily what we're talking about there is numbers. But with machine phase, if we go from single phase to three phase, and we've still got a 50 kVp X-ray beam, then our creation spectrum, for reasons that we'll talk about Friday, is going to start and stop in the same place, but we're going to have a slight separation in between. Really, it's, we've talked about this before. What happens when we go from single phase to three phase is the voltage waveform never drops to zero, so we get a higher average. And I'll tell you how that affects the emission spectrum on Friday. Okay, so we've got machine phase, we've got kVp, we've got mass. What else have we talked about this semester? And intensity. Mass. Fixed filtration, target material. Okay, voltage waveform we did. And I'm going to save filtration for Friday. I don't want to totally toast y'all this afternoon or this morning because she just got through a test. But target material. Target material, because the binding energies are different, our characteristic changes, but also because the nucleus is going to change. If we've got tungsten, it's that big. If we've got gold, it's that big. If we've got molybdenum, it's that big. Okay, the nucleus, let's say. So if we send electrons across the tube, if we had a gold target, which you're never going to use, but if we had a gold target, or even plutonium or something like that, something with a great big target, how much would it be easier to get those projectile electrons closer to the nucleus? The answer is yeah, it would. So what we're going to have if we change our target material, if we go with something that's a higher target material, our peak energy is always going to be controlled by the kVp we set. And what we're going to have is something similar to what we had, and it might not touch at the top, it may go further up that way. But what we're going to have is peak energy is unchanged. There's only one thing that changes peak energy, and that is kVp. That's why we call it kVp, right? So we've got 100 kVp, we've got a characteristic spike there, on the tungsten anyway. On the gold is probably going to be higher, right? Bigger nucleus, better binding energy on that inner shell electron. So if we had something that had a smaller nucleus, we went down to the molybdenum, got rid of the tungsten and the gold, and went down to the molybdenum, how much more difficult would it be to get those electrons close enough to the nucleus of that smaller atom to lose all of that energy? It'd be a whole lot more difficult, right? So fewer of the peak energies, and because it's such a small nucleus, it's going to be difficult to create any significant photons all the way across the board. So what we're going to have there is a creation spectrum. If we use 100 kVp, it's going to change it significantly. Okay, so these two are difference in target material. And of all of these, that's probably the least significant, so I'm going to erase it. I'm going to erase that one too. When we change target material, we change everything. But you're never going to change target material. The only time you're going to use a target that's not tungsten is if you go to work in mammography. That's the only time. Okay, so when you increase kVp, what do you increase? According to this, you increased from 50 to 100, meaning that the energy level increased, right? What happened to the numbers? What's the relationship between kVp and the increase in kVp and the number of X-ray photons we create? Okay. It goes up, and it goes up. There's a word for it. The square is it's proportional. It goes in the same direction, or it's a direct relationship. It's not proportional. It's exponential, right? So it's a direct relationship. As kVp goes up, the numbers go up, but they go up exponentially, right? So as we change from a single phase to a three phase, what happens to our numbers? This was single phase, that's three phase, and all of this area is numbers. So as we go from single phase to three phase, we get a increase, decrease in output. Increase. Single phase, three phase, we get an increase. Right. Okay. Mass. If we went with a change in mass, really with a change in mass, what we're going to see is something very similar to this. It's just going to change numbers. Mass doesn't change anything except for the numbers that we create. KVP, direct relationship, exponential. Exponentially proportional. Mass is proportional in every way. Okay. Filtration, again, we're going to hammer on Friday. Single phase, three phase, we're going to increase in output. And we'll talk about what else it affects on Friday as well. Okay. Questions? What questions do you have? Okay. So we're going to talk about this, to a degree, again on Friday in the lead up to what happens when we get a mission from the tube.
So, will we have this for sure on the final? Is there gonna be like a picture?
The pictures, no. If you have a picture, it may be two pictures where you compare the Brems spectrum and you determine which one's higher energy or which one has higher output or something like that. Yeah. So all of this, no. This is just explanation. Okay. All right. If no questions, then I'll see you on Friday. We'll start Friday at 8:30. Hopefully it won't be too long.
Would you say that a good portion of the test is like 7, 8, 9? Like the
I
ones
wouldn't
that we
say
haven't covered?
any more weighted towards 7, 8, 9 than other.
And you'd still say that the Angeles is still the best way to get information?
Yeah, the Angeles and the final review, which is should be in Canvas.
Yeah.
Yeah. Okay.